Hello everyone, welcome to my video. In this video, we are moving into chapter 3 and start to look at kinetics, where forces is coming into play. In the previous two chapters, we have built our foundations in kinematics when we did not care what's causing the move. By now, you should be super familiar, or at least familiar, with the four basic variables and all related equations, S, V, A, and T, or we usually say three variables because T is kind of embedded in them. They're changing with time. In this chapter, we will look at kinetics, where we need to analyze what is causing the move, the force, and we will explore the relationship between forces and acceleration. I like this quick illustration here. When we were dealing with kinematics, all we needed was to know what was the velocity and its direction. That's kinematics. Here in kinetics, now we want to know why the velocity is at 10 meters per second, not any other values, and by analyzing the force of this person is experiencing. This is kinetics. This is also a quick review of free body diagram. Please pause here to review as needed. If you still are a little bit rusty on drawing free body diagrams, we'll be doing a lot in this chapter. And chapter 3 is a long chapter. All right, let's begin. As I said many times, Newton's second law, F equals to ma, is the governing equation throughout this course. Just a little bit background here. The F over A ratio has been verified through many experiments to confirm that the ratio is a constant for the same object. But before knowing F over A is mass, the equation originally was F equals to Ca, and the C is the constant number representing the inertia of the particle, and not subject to changing velocity or acceleration. So the C part is not changing with anything. It's internal to that particle, to that object. It was later the preliminary form of F equals to ma appeared as F equals to Kma, and the K here is a constant used to account for unit consistency. Newton's second law is no doubt one of the greatest discoveries at all times, but it has limitations. It was not until recent century discovered that they only hold for certain conditions. Okay, generally speaking, Newton's second law hold for the primary or fixed inertial system and hold for any non-rotating reference system. But it does not hold for reference systems attached to the surface on Earth when the object moves too fast, or when the object moves over a large distance or long duration, and when we need high precision. However, F equals to ma can be applied to most movement on Earth's surface. Right? So this is what we really care about, but you need to know Newton's second law, despite its greatest discovery, has limitations. We briefly mentioned units in chapter 1. Here, let's take a moment to make sure everyone is on the same page, because from now on, this is going to be very important. We're going to use it a lot. F equals to ma in SI unit, force is Newton, given by kilograms and meter per second square. In imperial unit, force is in pounds, given by slug and feet per second square. It is when you're dealing with imperial units, you need to be extra careful to make sure what you're obtaining, as which is mass, which is force. For example, 1 pound, you need to check if it is referring to 1 pound force or 1 pound mass. If it's 1 pound mass, that is 1 slug. One of the most common applications of Newton's second law is calculating the weight. W equals to mg. Since the Earth gravity can vary from location to location, we already know that, the actual g value can change, but not by much, you can see in the g column. So, in this course, it is common in most scenarios, it is safe just to use 9.81 or 9.81 meter per second square as assumed standard value, unless otherwise stated in the question. Again, so if it's not stated, then use 9.81. If it's stated, use something else. I'm not going to trick you on that. Moving into section 3.3 now, talking about equations can be used to solve problems. F equals to ma, of course, the basic 4 steps I like to recommend to anyone at the beginning are draw the free body diagram, do the force balance. You can break this into necessary coordinates, x, y, nt, or r theta, and apply Newton's second law on the resultant force, and then apply necessary equations or solve the necessary equations to solve those variables you're interested. Generally speaking, if you are given the acceleration, use F equals to ma to calculate the force, or if you are given the force, you want to use F equals to ma to calculate the acceleration. Okay, so either way, you're from left to right or right to left. We discussed about unconstrained motion and constrained motion before already. However, here we want to do a quick review before moving on. For unconstrained motion, such as flying ball or free fall object, the path is determined by its initial velocity and the force acting on the object. That's it. It's unconstrained. Okay? That's the only two determining factors. As for constrained motion, similar to what we talked about connected particles, the object's movement is restricted. This is what we call fully constrained. On the other hand, we can also have partially constrained motion, such as here we throw a rock onto the wall. It is at the brief moment when the rock hits a wall, the motion is constrained. And another example is train tracks. Train tracks is considered fully constrained. Okay, so you can have constrained motion, fully constrained, or partially constrained. Theoretically speaking, what we did so far can be applied to any scenario from 1D to 2D to 3D. But as you should know clearly by now, we will be focusing on dealing with 2D motions in this course. So what a relief for many people. With probably 1 or 2 exceptions. Okay, I don't want to close the bridge. Probably you'll see 1 or 2 3D, but should be straightforward enough. Let's start with looking at rectilinear motion with F equals to ma. The general steps listed here is intended to be exhaustive. Okay, we will start with set up proper coordinate system, x, y, z, and break forces or movements into proper components. Then we'll apply the F equals to ma or F equal to 0 if it's in a steady motion or at rest. Step 4, solve for each component, and number 5, finally combine all components as necessary, because sometimes you are asked what is the velocity on the x direction versus what is the velocity. Okay, velocity means the overall velocity. Velocity on the x direction means vx. Okay, this is an exhaustive list. Follow them, you won't miss anything. All variables, as we know, can be projected onto different axes and analyzed separately, then put back together. You can either do scalar analysis for simple, straightforward scenarios, or use the vector format for more complex problems. To be honest, I usually prefer the vector format even for simple problems, since it always guarantees the direction, so I don't need to worry about the direction once I set up the coordinate system, and then I just read the vector. Please pay attention to what the question is asking, whether it is asking for an acceleration for a specific direction or the total acceleration. Same applies to force and velocity. I copied this page from section 2.2, should be familiar to you. This is to remind you that all equations we developed there in chapter 2, you will see them again here. All equations we use in chapter 2 still applies here as soon as we break the motion into individual axes. So you should be very, very familiar with them now. If you need to review them, please take a time to do so. For example, looking at this person skiing, we want to analyze its motion. To do so, we will first set up the reference system, or the coordinate system. Normally, a horizontal vertical xy system is used. We can do this here. With the reference system, then we'll do our free body diagram. We start with gravity is a mass, and there's a normal force because it's contacting the surface, and then there's the external force, the drag force. In this case, we'll ignore the frictions just to simplify things, so we end up with 3 forces acting on this person. Remember I said, we need to improvise sometimes. We don't want to complicate our life. With this horizontal vertical xy system, when we break forces onto x and y, we need to do this for Fn and F drag. Therefore, if I set up the xy coordinate system at an angle the same with the slope, I only need to break the weight into x and y components instead of breaking two forces for a sloped or at an angle reference system. I only need to do this for one force. Then on the x direction, we can apply F equals ma to calculate acceleration and velocity if we take integrals of it. Generally, once we have the free body diagram and equation, we will just solve the rest using whatever mathematical skills as needed, plus the boundary conditions that they are provided in the question. In the list of recommended readings for sample problem 3/5, it is not required. You can still read it, but I won't test you anything like this. Okay, thanks for watching. I'll see you next time.